Actually, the spirit that we're going to follow in this second hour is again very much in the spirit of keeping our friend George Green happy, because we will develop monkey tricks to find solutions in some circumstances. And we're not going to be quite sure that what we do is correct until the end, when we do find the solution that fulfills the boundary conditions. And then we're happy, but we're only happy, you know, in the end, not during, right? So there are many, many methods to solve Laplace's equations, and perhaps the most powerful in many, many circumstances is called separation of variables. Have you done separation of variables in mathematics when you've got multivariable functions, etc.? So you already kind of know the idea, right? The kind of Platonic idea behind separation of variables is, as per the title, you separate. So if you have one equation, which is a multivariable equation in the sense that the solution that you're looking for depend on multiple variables, then it's kind of annoying. What you do is you hack it into pieces, each piece depending on a single variable, okay? But that does not work in all circumstances, and we will discuss a little bit the circumstances in which it works. Now, in order to make this, you know, concrete, I will do a little example in Cartesian coordinates, but we will spend most of our time discussing spherical coordinates, which is, you know, the more powerful thing. However, most of the, all of the important ideas are in the Cartesian case. So, best to just do a simple example, actually. And this is an example that was actually lifted out of the Griffiths book. So if you have that, you'll recognize it. So what do we have? We have a three-dimensional world. However, this three-dimensional world is sliced in two places by infinite planes in the XZ plane. Okay, so X, Y, Z like this. And I imagine that at Y is equal to 0, I have an infinite plane. So here, you know, just all the way here and at the back and everywhere else, there's this infinite plane at Y is equal to 0. And there's another point, Y is equal to A, where there's another plane. Okay, and again, it goes like all the way. Okay, so again, with my fabulous drawing skills, you see exactly what I mean. Okay, so the additional condition is that at X is equal to 0, there's a boundary, okay? There's an infinite insulated strip that we were going to keep at potential phi 0 of Y. And here I insist this is a given function. Oh, this thing. That's the name for that gizmo, isn't it? The zoom thingy. There are many zoom thingies. Okay. Yeah, that helps, doesn't it? Thank you. Okay, so what am I saying? I'm saying that, you see, at X is equal to 0, you see this this kind of strip in here. Yeah, maybe I'll. So this thing here throughout at X is equal to 0, going down infinitely, right? So I keep it at a fixed value of the potential, and I'm not telling you what the numerical value it is. It's just tabulated here. You can look it up. However, it's a given for you, phi 0 of Y, when the evaluation point is X is equal to 0. And the question is, what is phi between the plates? Okay, so what that means, i.e., phi of x, y, z for y between the plates. Okay, so I want to know the value of the potential somewhere between the plates, yeah, between my two infinite plates, closed off. Okay, so it's just like a setup like this. Okay, so what are we going to do? Well, we're going to think. And what is the best way of thinking? Throwing the kitchen sink at it all. So what do we have? Well, you've given me, or I've given you, boundary conditions which don't depend on Z. Okay, so that's a very important fact here. You see, although we're in 3 dimensions, there's no Z dependence in my thing. So therefore, really equivalently, I'm solving a 2-dimensional problem. Okay, so essentially no dependence on Z. So it's equivalently the 2D problem. Okay, so what I'm going to write is Laplace's equation in 2D. And that's going to be that the, I'll write partial derivatives here to be clean. The second derivative with respect to x of phi of xy plus the second derivative with respect to y of the same thing has to be equal to 0. Okay, and then if we want to be clean, we can write our boundary conditions. Let's write our boundary conditions so we can refer to them later. Actually, I should also tell you that the plates are held at fixed 0 potential. That's an important element. So let's write all of these. So I've got the first condition, which is that phi of any x with y is equal to 0 is equal to 0. Okay. And the second condition is that phi of any x with y is equal to a is also equal to 0. Okay. Yeah, so at y is equal to 0, a phi is equal to 0. Yeah, that's part of the given here that I'm just putting in a clean equation here. Then there's the third one. Phi now of x is equal to 0 for any y is given by, so that boundary here, the kind of strip that we have here, and I told you that this was this given function phi 0 of y. Again, it doesn't matter what that is. The only thing that matters is that it is known. It's a given. It's an input to the problem. And now, of course, the other condition is that if I was to walk all the way to infinity in the x direction for any y, then this would go to 0, right? I don't want that thing to go to crazy values as I walk away. Okay, so this is the mathematical statement of our problem. And you see, this is exactly a mathematical statement which fulfills all the prerequisites for invoking Green's theorem and the uniqueness theorem, because we've got the Laplace equation, and at each boundary, I'm giving you, in this case, Dirichlet boundary conditions. So you're happy, you know that there's a unique solution to this, if it exists. Okay? So here goes the kitchen sink. What are we going to do? Well, annoying, you know, XY dependence and whatnot. Wouldn't it be great if it happened to be the case that life was friendly to us for once, and that the function of X and Y that I have here really is the product of two different functions. One function, big X, which depends only on X, and one function, big Y, which depends on Y. It absolutely does not have to be the case. This is an ansatz. This is an attempt. This is like a guess. This is a, you know, why not? Okay. if we use this now, we can try to see if we can come up with a solution. If we can, then it's great. So what do? We plug this into Laplace. And what does it give us? Well, you see, first of all, the partial derivatives on this function of two variables becomes total derivatives on the appropriate function here. So the first term, I'm taking derivatives with respect to x, but y does not depend on x. Therefore, this first term here just becomes the second derivative, total derivative now, of big X times y. The second term here, I take derivatives with respect to y, but not with respect to x. X doesn't depend on y. And then I've got the second derivative of the y function with respect to y is equal to 0. Okay? Everybody happy? So what I can do is I can just divide by xy is equal to 5, right? And what does that give me? It gives me that 1 over x d2x divided by, sorry, dx squared, plus 1 over big Y d2y dy squared is equal to 0. Okay, because I'm looking for a non-zero solution. Certainly I've got non-zero solutions here because of this this boundary here. And in that case, I can divide by that thing. Can't really divide when the potential is 0, but still works out. Okay, so what's now the point of a separation of variables is that this is only dependent on variable x, and this is only dependent on variable y. Okay. Therefore, if I change y, the value of this one does not change, but still I have to fulfill the thing. And if I change the value of x, then this changes, but this cannot change. So the only possibility is that these two terms, independently from each other, are equal to a constant that then has to add up. So only possibility this thing is equal to a constant, and then you make a choice for a convenient constant, but you rewrite it as a differential equation of second order for this thing is equal to some constant, and then this constant, by for fun, is just going to be written k squared times big X, and then this one here would give you that the second y derivative of function y would have to be minus the same constant. Okay? So in that case, this is equal to k squared, this is equal to minus k squared, so then this is equal to 0, we're happy. Okay? But now we've simplified our lives because we have to solve these equations here. Okay, so let's just proceed. Yeah, what is it? So solution. So let's call this 1. Let's call this 2. 1 as a solution. Well, you've guessed it. Essentially, I can write that x of x is just some constant with an exponential e to the kx. Plus another constant b e to the minus kx. Okay, that's your like most general solution for this. 2. Well, it's the same thing, but with a different sign here. So then it's just a question of putting an imaginary here. So we could have e to the ikx, e to the minus ikx. Conversely, we can just use sine and cos functions. So here, the y function as a function of the y variable would have to be a combination of, say, sine of ky plus another constant d times the cosine of ky. Okay, so so that's it. We've now solved the Laplace equation in the bulk of the space between our two plates. what remains is to verify that we can indeed fulfill the boundary conditions. Okay, now the first observation is that, well, I can choose lots of different k's here if I want to and linearly combine them, because again, by superposition, I can just stack up as many independent solutions as I want. Okay, and here is where the discussion becomes a little bit more profound. The idea here is that we are writing these differential equations that in general generate for us a family of functions that has really the interpretation of a kind of linear vector space, in the sense that there is a space of functions that is achievable, and these functions can be written, every single one of them can be written as a linear combination of basis functions that fulfill the basic things. Okay? You've seen Fourier series. So what is a Fourier series? A Fourier series is a simple basis representation for a generic function that has a certain periodicity. You give me periodic functions inside a certain interval. By Fourier's theorem, I can write whatever function you give me here, provided it is periodic, as a summation of basis functions, each of which is individually periodic and which I can hook up with different amplitudes in order to reproduce your function. Okay? So there's the idea of orthogonal functions here, and a complete set of orthogonal functions. So you have that for the sine and the cos here, because you've just got some periodicity built in. Okay, so here that's a little bit what we're doing. Okay, so what I can imagine is that I could say for the solution of x, have a certain label, say a little n here, and let me give a little n here, and then I would have a little yn as well here. And then I would still be good if each time I put in the function xn, I also put in the function yn, because those two have the constants kn squared and minus kn squared, which add up to 0. But I could choose many different values of this k as well. And as long as I always put those functions, then the sum of the constants is also going to be 0. Okay? Question?
And it's not unique.
It is not unique yet because we have not fulfilled our boundary conditions. It's the boundary conditions that will fix the unique solution. At the moment, what we're doing is that we are writing all the possible solutions to all conceivable problems in that particular geometry. Okay? And then, of course, there's no uniqueness. There's like anti-uniqueness. However, by the uniqueness theorem, once you give me the boundary conditions, then it falls back down to 1. Okay? So we are busy at the moment writing the most general solution that we can have for this. So what I would imagine is that I have an xn here with an an and a kn and a bn and a kn, and the same thing yn, cn, sine kny, dn cos kny, and then the general solution for x would just be, if I choose these parameters here, it would just be the summation over all these available n's of the xn that I will choose. Okay, so rather the xy that I have, so the phi would become the summation over n of the xn times the yn, etc. That would solve all of this thing. Okay. So let's just do our work here. We're going to try to fulfill boundary conditions. So boundary conditions. So let's proceed systematically. So let's see. So the fourth boundary condition, namely the one that if I take x to infinity, I want to go to 0. That means that I will like to put the an to 0. Okay, so this one means that I will like to put these a is equal to 0. And then the first one, going back here. So the first one was that when I go to y is equal to 0, I want the whole thing to be 0. But when I put y is equal to 0, the cosine is 1, the sine is 0. So the d has to be 0. So this condition here means that my d is equal to 0 here. I want to put, so any function has this 0 here. Okay. Then I should almost have 2 pages here. You see the second condition here, you see now the evaluation y is equal to a also has to give me 0. Okay, so from 2, that phi of x and y is equal to a is equal to 0, this tells me that I always need that the sign of kna, I always need this to be 0. Okay, so really, what does that mean? It means that I can choose my kn to be equal to just multiples of pi over a times n, and then here the n I will choose on all meaningful values, 1, 2, 3, etc., etc. These are all allowable. Okay, so up to now. Up to now, what we have is that our phi of xy has to be this summation of overall n's of the xn yn of y. So let's write this. So I have a summation n is equal to 1 to in principle infinity of now let's just use this constant here as the parameter if you want that. I'm multiplying the 2 functions, so really if I multiply the 2 constants, I just get another constant. Let me call this particular multiplied constant Cn here. It doesn't matter because I can only fit one number. E to the minus knx and then sine of kny as our solution. Right, so really that's what it is, and you know, kn is just defined in here, right? So that's our general solution. Now, the last step is to fulfill the last boundary condition that we have. So last step, it's boundary condition 3, is it? And this one told us that phi at x is equal to 0 and y was equal to phi 0 of y, which was a given function. Okay, so what does that mean? It means that the summation n is equal to 1 to infinity of Cn, now x is equal to 0, so this is just not there, sine of kn y has to be equal to phi 0 of y. Okay, so that's the thing. Now you see here we will invoke the orthogonality relationship of our basis functions. Okay, just like in Fourier series, we know that sine functions of different characters here are orthogonal to each other, unless these things like resonate with each other. So there's a relationship that we can use. We can use the integral from 0 to a of a certain thing using y. So let's do that. And then what we have sine of, let's do it explicitly. So let's say I have a little n pi y over a. And then I have a sine of m prime pi y over a. Okay, so this is a an integral that you've learned how to do when you did the Fourier series. So this is just going to be a over 2 with the Kronecker delta between the indices n and n prime. Okay? If they differ, these things resonate against each other. If they coincide, they interfere constructively and give you a finite answer. Okay, so these are all basic things. So I need to back engineer the coefficients Cn. So what do? I take this relationship here, I multiply by sine of kn prime y, and I integrate over y. Okay, so let's do this. So here's what I want to do. I'm just going to use this one, and I multiply by I'm going to do integral from 0 to a dy. Then I'm going to multiply by a chosen function, which is sine of k n prime y. Everything I've got here or everything I've got here. So on the left-hand side, I get summation n is equal to 1 to infinity. Different indices, right? N prime, n. Don't ever use the same index in multiple summations in my presence. Okay, that whole thing has to be equal to the same integral on the other side. What's the integral on the other side? It's the same thing, same integral, 0a dy, multiplying by the same function, which is the sine kn prime y. But now I'm multiplying phi 0 of y, which you don't know. But if you were to know, you'd be able to compute this integral. Now, the point is that I can invert the summation and the integral here under assumptions, very mild assumptions in this case of convergence, which are manifestly obeyed here. And what it gives me is summation n is equal to 1 to infinity of Cn. But now I have the integral dy of sine kn prime y times sine kn y, which is exactly what we wrote down here. And that integral is just a over 2 times the delta of n with n prime. Question? N prime is also an integer. It is essentially my chosen integer that I throw here, whatever it is. Okay. And so you see, then this so this is equal to this, which is then equal to, I can just resolve the thing, because now this is just a over 2 c n prime on the left hand side. Okay. But on the right-hand side, I get this very integral here, 0a dy, sine k n prime y, phi 0 of y. So said otherwise, by exploiting the orthogonality of our basis functions, solving our Laplace equation in the volume considered, we have an explicit expression for the coefficients Cn in terms of an integral of the information that we have. Okay, so that's your answer. And now it's just sine k and y, phi 0 of y. Okay, what I want you to see here is this procedure in multiple steps. First, we have written down our problem properly. We've exploited a symmetry, no dependence on z, cost z out. Then we have looked at our boundary conditions available on all boundaries. Green happy. Then we have said, I don't know how to do this. Let's just imagine that the world is friendly. Let's just suppose that this x and y dependence factorizes into a product of two things. Doesn't have to work. I'm checking if it works. With this form, you write down the decoupled equations. You give the most general solution to these equations. And then you go back to your boundary conditions, trying to see if using superposition, so linearity of these things, if you can fit your boundary conditions by combining these various orthogonal functions together in order to fulfill your boundary conditions. And this is just what we have done here. Okay, but again, distinguish the kind of strategy from the details. This is the idea. So this is the solution to our problem, because now for any function phi 0 of y, which you explicitly tabulate for me, I can compute these coefficients. And now I have a solution to Laplace, which fulfills all your boundary conditions. And I don't have to do work anymore, because I know that if I've got a solution, that is the solution. There's nothing else. There's nobody else. So I don't need to lose sleep at night wondering if my factorization into function of x times function of y fails. It doesn't. It works. Question?
So my question is, it makes sense from a physics point of view why there's only one solution to this system. But my question is, how do you know that also people show mathematically that there may not be a solution which does not have a separation periods?
Yeah. So the question is, so physically it makes sense, but mathematically, does it really make sense? And really, I urge you to spend an evening with George Green, going back through the details here, because this is exactly what he is telling you. He is telling you that mathematically, there is no other function that will distinguish itself from your first solution besides a constant shift. All the other functions that you can possibly conceive, they map directly to the one solution you have found. They can only differ by a constant, and then only if you have Neumann conditions. So I really insist on this. The Green's identity statement is a mathematical statement. It is only contingent on the existence of the derivatives and on the convergence of the integrals, which we take for granted. Follow-up question?
So that's shift you described?
Yeah.
Is that A into a H?
No, it's akin. So the question is, what is this shift that I'm talking about here? It is exactly the manifestation of the arbitrariness of the origin point from which we determine the potential. You remember when we first defined the potential, we said you integrate from a certain, reference point. It is only a shift of that point. That's what it is. So only potential differences are physical, because the only physically measurable thing is the field. The actual value of the potential, if it's shifted by a constant, it leaves the gradient unchanged, therefore the field unchanged. So this is the only arbitrariness here. And I insist it's also an arbitrariness only if you give me Neumann boundary conditions. Because if you give me Dirichlet boundary conditions, then there's no shift. Got absolutely everything there. Yeah?
Could you state the final value of
yes. So you see the so phi of x and y is equal to summation n is equal to 1 to infinity of this Cn. Yeah, so really this one here. So this is a number that you can compute for each n. E to the minus, I can write it explicitly in terms of the n pi x over 8 with sine of n pi y over 8. This is your solution. Okay? Okay. So this is separation of variables in Cartesian coordinates. Question? Okay, I went a bit fast on that. The question is, where did the Bn coefficient go? Here, indeed, I kind of skimmed a step, because we wrote most general solutions in terms of two sets of two functions, a, b, and then c, d. Using the boundary conditions, we required that the a's were 0 and the d's were 0. And therefore, the only relevant contributions were coming from this function times this function. And you see, when I multiply these two things, yes, of course, I've got these two constants, B and C, multiplying each other. But that doesn't give me more freedom. I still have only just one coefficient to put in there because there's only one function left in both cases. So then we say we don't lose any generality if we put B is equal to 1. And then we fit the C. It doesn't give us anything else to keep the B. Right? So that's what we did here. Okay? So that's the case for Cartesian coordinates. Is everybody happy with the philosophical approach to separation of variables? Yeah? And again, I emphasize, this is not constructive. It is not starting from the state of problem and walking linearly, going to the solution in inevitable steps. This is not what this is. Separation of variables is you've got the problem, and then you take a walk in the park. You say, oh, let me try that way. Yeah? And, you know, you're looking for the castle. Let me try that way. I don't know where this is going, but I'm going that way. I don't have to go that way. I could go this way. I could go that way, but I'm going that way. And if I find the castle going that way, then that is the one castle. So it is not constructive in the sense inevitable. It is one attempt. You can cook up problems where it doesn't work. But typically, the problems where it doesn't work, you recognize from the very beginning because you maybe misinterpreted the symmetry of the problem. If the required symmetry is present, then actually it will work. Okay, so that's the general statement. Okay, so that was separation of variables in